Thank you, Antonis. Thanks a lot. Just waiting that the slides come up. Just let me thank you for the invitation. And so, yes, as Antonis was saying, I'm really happy to tell you today about a project we started now already 5 years ago. And the topic is AGN outflows. The redshift range we have been focusing is called cosmic noon, which means redshift between 2 and 3, which, as you know, is the peak of star formation, but also the peak of assembly of mass on supermassive black hole. So a very interesting period to study in the cosmic history. And apart from studying the physics of the outflows, what we were interested was also to try to understand if these AGN-driven outflows have an impact on their host galaxies. And as Antonis was saying, I've been using mostly the ISO facility, and this is just two pictures of the facility that we've been using. On the top, you can recognize the VLT in Paranal in Chile, and on the bottom, there is the ALMA array on Cenantoro, still in Chile. So, yes. But AGN feedback, as I mentioned a few times, is a topic in a much broader context that is actually the one of understanding how galaxies evolve through cosmic time. This nice picture that I'm sure you've seen many times in talks is from a nice review by Tumlinson now 4 years ago. Depict the picture what we call the baryonic cycle of matter and gas in the universe. And the baryonic cycle is, if you want, a collection of different physical processes and mechanisms that govern the formation, but also mostly the evolution of galaxies through cosmic time. So we have process, as you can see, and let me just change the pointer to a last pointer. You can see there are accretion, possibly accretion streams of cold gas from the cold galactic medium into the galaxy. Then there are physical processes that essentially regulate the transformation of this fresh gas into stars. Of course, also regulate the accretion of gas into the central supermassive black hole. And then finally, there are also processes which involve both star-forming processes like supernova-driven winds, but also the so-called AGN feedback, so feedback from the AGN, that may redistribute gas, eventually expel gas from the galaxy back into the medium. And gas that is, in this case, may be not anymore metal poor, but actually enriched with metals and materials from star formation process. So this is the broad context in which we want to study the AGN feedback. And in fact, this is a field that has been active for many years, I would say at least 20 years. But AGN has been given, in many cases, the role of, say, main actor in this play. And it's easy to understand why, if you think about the energy that the AGN is able to release into the host galaxy through cosmic time. So this is, again, of course, an artistic impression, just to picture the central region of the AGN, pretty close to the black hole, in which there is the accretion disk, and we know that winds can originate from the accretion disk. As you can see, also, there is a jet, a strongly collimated charged particle emissions. In both these, the winds from the accretion disk and the jet are able to release energy that is order of magnitude larger than the binding energy of the host galaxy itself. So in principle, the AGN is able to provide energy that can heavily affect the galaxy and also its evolution. Of course, we have to always keep in our mind that we are doing a huge jump in physical scale. The picture I showed you before was 100 kiloparsec, and here instead we have to zoom in at least 7 orders of magnitude to get into this very central region of the AGN. So, and is this for this reason, I mean, the ability of the AGN to provide so much energy that the so-called AGN feedback has been extremely used in cosmological simulation. And this has been essentially essential for the simulation to reproduce observation. On the left, there is a plot, a classic one, to just make this point, in which you have the distribution of the stellar mass as a function of the halo mass. And if you do run simulation without any feedback prescription, you will be up here. So you will overestimate largely the amount of stellar mass in galaxy, which is the cyan region here. It is only when you switch on star formation feedback recipe, like supernova-driven winds, that you bring the low mass hand back into the regime that you observe. But then you have to invoke AGN feedback at the high mass hand, where the potential well is so strong that the supernova-driven winds cannot do much, to bring back the simulation result in agreement with observation. So as I said, this is why AGN feedback is being so popular, because it provides you all the energy you need to do this job. But one thing is having the energy available, and another thing is actually to couple this energy with the surrounding medium. So it is very important to understand also how much of this energy provided by the AGN will be able to couple to the gas and dust surrounding the AGN, so that actually can have an impact on the Earth's galaxy. So now let's focus on AGN feedback, in particular on one incarnation of AGN feedback, so the so-called AGN-driven outflows. The first thing we need to say is that outflows are a physical phenomenon that involve many different physical scales and also different gas phases. So let's start from the very center, close to the black hole, the accretion disk I was showing you before. And we have observed, mostly in the X-ray, highly ionized accretion disk winds, so-called UFOs, ultra-fast outflows as well. These are essentially highly ionized gas that is traveling at velocity mildly relativistic, 0.1, 0.3, the velocity of light, and are usually observed as you can see, an absorption feature in the X-ray spectra. This is a clear case from a local quasar. These strong ionized winds close to the center of the AGN are quite common actually. From archival study using XMM, for example, we know that there is a lower limit of at least 40% of the local CPER that do show such powerful outflows in the proximity of the AGN. If we now move to a different gas phase on a larger scale, we know from millimeter and sub-millimeter observation that there are winds in a cold molecular phase. Usually here the tools are CO lines that are lines that you can observe easily in the millimeter, sub-millimeter. And if you look at the reddish line here for Marcanium 231, you would realize that the line profile is not a simple Gaussian profile, but has these winds here at high velocity. And this is essentially a signature of the fact that the gas that we are tracing is not at systemic velocity, but is actually outflowing. And this is, has been observed in many different objects at different redshift, up to very, very high redshift, AGN redshift of 6 or so. And then there is also the ionized and atomic gas phase. And this is what I will mostly talk about, because this is what the survey I will present has been observing. And you use, in this case, optical or near-infrared observation, depending on the redshift of the object. And the tool you use to trace this gas is now these O3 lines. And again, you see that the profile is not a simple Gaussian, but this has a broad component. And again, the interpretation, the physical interpretation is that this broad component is tracing gas not at systemic velocity, so it is moving through the galaxy. If you are observing local objects, especially, you can use integral field spectroscopy to have actually a picture of the outflows ongoing. And this is nicely seen in this object, observed with MUSE, that is an optical integral field spectrograph, the VLT. And you can recognize for this local CFERT, the galaxy disk in red. This is traced by H-alpha. And beautifully, these biconical shape outflows traced by O3. So, as I said, outflows involve different scale and different gas phases. So in order to understand the physics and understand also the impact of the outflows, what you want to do is to sample this different scale and different gas phases. But in terms of modeling, what how do we believe that these outflows are actually generated and driven? There are different models in the literature. The most popular one is the so-called wind-driven outflows, in which you start with subrelativistic outflows, 0.1, 0.2 C, in the very center, pretty much what I was describing before in terms of ultra-fast outflows. These outflows shock the medium at a certain distance, and this creates two shocks. Reverse shock that go back towards the AGN and slow the winds, but a forward shock that essentially couple with the surrounding medium and generate an expanding bubble that go through the galaxy. Now, if we are in the so-called energy conserving regime, which means the energy is conserved, then this expansion is really like an adiabatic bubble that go through the host galaxy, transferring energy and momentum from the wind to the surrounding medium, gas and dust. Eventually, this wind will cool down, and so this is the way you explain the molecular phase of the outflows, because the gas will cool and will form molecular clouds. So if you want, this model is able to explain the different outflows I was referring at the beginning. A very fast suprarelativistic outflows in the center, the ionized phase when it's warmer, and then finally a colder phase when the gas cools down. As I say, this is a very popular model, but it's not the only one. And in particular, there are many models that invoke jets as the main driving mechanism for outflows. And although I will not talk about jets, I definitely need to say that we should not neglect them as a possible source of these outflows. And there are two nice examples here I want to show you. On the left is from the group of Raffaella Morganti, and they have observed different radio loud quasar. In particular, this one is Douglas-Seifert. You can see that there is a nice radio jet. This is the contour in gray on the top left. And this is the core of the jet. And this is what is called an hotspot, meaning the region where the jet collides against the medium and shock. The nice thing is that if you go to the bottom right panel, and if you observe the same object with long-speed spectroscopy, tracing some H2 line, you see that where there is the hotspot, there is a cloud of gas that is not a systemic velocity that will be here. And you can see this also in the line profile. So what it's telling you is that exactly where the hotspot is located, you observe the presence of molecular gas, in this case, that is turbulent, disturbed, and is not at systemic velocity. So this is, I think, a strong hint that the jet is actually originating that perturbation, that turbulence in the gas, and so has something to do with the generation of these outflows. On a statistical sense, the impact of jet on outflows, you can see also on the top right. This is work by James Mullane a few years back using the Sloan. And this is the cumulative fraction of object with a certain full width of the O3 line. The idea is that the larger the full width, the larger is the fraction of gas that is moving and not systemic. So it means that these are outflows. And so if you compare the blue and the red line, the blue is for object with low radio power, the red line is for object with high radio power. You can see immediately that the objects that mostly have outflows are also radio power, which again, statistically speaking, make a link between the presence of the jets and the presence of the outflows. And finally, at the bottom is a work by Miranda Jarvis. She was a PhD here at TISO, and this is a local Seifert. This is an object for which we know that there is a jet. It's not a powerful jet, and these are the bluish contour you see here. And the background map is an O3 map in which essentially the purple values show you where the gas is disturbed. Again, there seems to be a spatial correspondence between the location where the jets bend and so hit the medium and where you have disturbed gas. Again, in a hint that the jet has something to do with the generation of the outflows. Okay, but as I mentioned at the beginning, AGN feedback has been widely used in simulations, and the reason is that there is a lot of energy available, of course, but the recipes that you find in the literature are extremely there is a large variety of recipes in which simulation have implemented AGN feedback. Just to give you a few examples, on top you have the result from the so-called TNG simulation. Is a large cosmological simulation done next door here at Max Planck Institute for Astrophysics. And what you see here is a snapshot of an outflows, an AGN feedback going through times. And what I want to mention is that they have essentially injected two recipes of AGN feedback depending on the Eddington ratio of the AGN. When the AGN is accreting at low rate, then they have what they call kinetic wind. That means essentially a pulse of very collimated energy. Instead, when the AGN is accreting at high Eddington ratios, then there is essentially a continuous thermal energy injection. We will see later on why this is important, because there's a very different predictions on the observable, as we will see at the end of the talk. On the bottom left, there is another model in which essentially the transfer of energy happens through radiation pressure on dust. This is very nice work by Tiago Costa. And of course, as I said, jets can also be invoked also in simulation as the trigger of the outflows through the injection of mechanical energy into the gas. Okay, but this is a field, as I was mentioning, that has been active for 20 years, but there are many open questions still today, and definitely 5 years ago when we started this project. And so I just listed here 3 questions that I would like to go with you through the talk and possibly find an answer, or at least improve our understanding of those. And the first one is we want to understand how common are these AGN-driven outflows, especially redshift 2 to 3. The second one is that we would like to understand if there is a link between the energetics, the property of the outflows that we measure, and the properties of the central supermassive black hole. This is important because allow us, first of all, to be sure that these are AGN-driven outflows, that AGN is doing the job, but also that allow us to distinguish between different physical models on the driving of the outflows itself. And the final question actually is to go back to the original picture and to understand is these outflows have actually an impact on the host galaxy. The impact could be in terms of gas, and ultimately also on the ability of the host to form new stars. And so I've been using as a tool mostly integral field spectroscopy. Integral field spectroscopy has the clear advantage that you combine spatial and spectral information on the same object. I've been mostly using 3 instruments and 3 different surveys that just show you here. The first one is the yellow one is at low redshift, cover a relatively wide range of volumetric luminosity, and use MUSE. This is an optical interferometry spectrograph, the VLT. Then there is a more broad redshift range survey between redshift of 1 and 2.5 named CASH-Z that use KMOS. And finally, the survey I will tell you about is this reddish box that use symphony, so in the near infrared, because the O3 line is in the near infrared, the redshift of 2, and it covers a wide range of volumetric luminosity. So let me tell you about this survey. The super survey started, as I said, in 2015, and it's a medium-sized collaboration, as you can see. I have highlighted in red the PhD student or young postdoc that did produce most of the work that I will present you today. We finished the survey already since 1.5 years. The observation were essentially 280 hours at VLT. And the most important thing is that this observation use adaptive optics. And this is important because adaptive optics allow you to resolve a smaller scale of what you would do without such a correction. And so in our case means going down to PSF of the order of 0.2 a second, which if you translate in physical scale ratio 2, means that you are able to resolve of the order of 2 kiloparsecs at that redshift. It's a blind survey, so it means we didn't select target except to be X-ray AGN. The targets are coming from the usual X-ray surveys in the wide or deep density beam survey that are in this redshift range between 2 and 2.5 that allow us to observe 2 lines, mostly O3 in the H-band, and this will be our main tracer for the ionized outflows, and H-alpha in the K-band that we will use to trace star formation. On the right panel, you see how our survey compared to other. I mean, we cover a very wide range of volumetric luminosity, but most importantly, in this other plot, in which in the y-axis you have a spatial resolution, it's useful to make the point that super, this red box, is pushing the spatial resolution to lower value of what usually was done at this redshift, and this is very important. This is again to show you the range of parameters that we cover in the survey. On the left, you can see that we cover essentially 4 order of magnitude in volumetric luminosity, but also that we are sampling both a wide range of column density. So from type 1 unobscured AGN up to heavily obscured object. And the right panel is just to show you that the range of Eddington ratio that we sample is essentially from 1% of Eddington up to Eddington. So it's a wide range of accretion rate. These are the usual survey with, deep field with a lot of photometry like Cosmos and CDFS. So this has the big advantage that you can do very good CD fitting. And as you can see an example here on the left. And this is important because apart deriving the volumetric luminosity of your AGN allow you to calculate stellar masses and star formation rate. But then you can use, as we did in the right panel, to put our object into the so-called main sequence plane. So you have here star formation versus stellar mass. Our object are the color object, and this thick black line is the main sequence at the redshift of 2 and 2.3, the mean redshift of our survey. And so you can appreciate most of our objects are in the main sequence with a few objects above and a few below it. So we are mostly sampling the main sequence. Okay, now let me bring you in a tour, if you want, of the outflows that we observe going through those different scales I mentioned at the beginning. So let's start from the very center, the so-called Broadland region winds. So we are on sub-parsec scale. So one thing that is very well known in the literature is that if you compare, as is done in the left plot, the full width of the carbon-4 lines, that is rest frame UV lines, with the full width of the H-alpha, H-beta, the correlation is extremely poor, which is usually attributed to the fact that the carbon-4 is not tracing gas, virialized gas, but actually tracing gas that is moving, outflowing. And so this is essentially a very bad feature for carbon-4 if you want to use carbon-4 as a black hole mass estimator, as you do with H-alpha and H-beta, but it's actually a nice feature if you're interested to trace outflowing gas. And so the idea is that you can observe the carbon-4 lines, as we did, and you can recognize that this asymmetric profile can be again be interpreted as a superposition of gas at systemic and gas outflowing. So we will use the carbon-4 lines to trace the outflows on sub-parsec scale. What is driving such outflows at this small scale? This is a nice collection done by Justina Dietri a few years back, in which you have on the y-axis the velocity of the carbon-4, so the velocity of the Broadland region winds, as a function of the volumetric luminosity. And she found that there is a nice correlation between the two, reported here, which is consistent with what you would expect from a radiativity-driven winds. So this is driving these winds is radiation pressure. We did a bit more study in detail inside our survey, still with Justina. And here you have the equivalent width that we measure for this line as a function of the velocity of the line, and so of the velocity of the wind. Our object has this colored object, and the color gives you the value of the alpha x. So you know that alpha x is the ratio between the 2 keV and 2500 astron luminosity. So it's essentially a measure of the hardness of the radiation that the AGN is injecting in the surrounding medium. So what we see is that actually the acceleration processes seems to be related strongly with the hardness of the radiation. What we mean is that if you consider object with a larger value of alpha x, so say we did a cut at minus 1.6 roughly, so you have a harder SED, so which means that for a given UV luminosity, you have a lot of high energy ionizing photons. And so this results nicely in a large equivalent width of the carbon-4, which is consistent with the fact that you have a large amount of ionizing photons, but with low velocity. And this, we believe, we speculate, that is due to the fact that this gas is actually over-ionized by all these photons, and therefore there is not a very effective line driving mechanism. The opposite happens if you look at the reddish object, the one with the lower value of alpha X. So here the SED is softer if you want. So there is a deficiency of ionizing photons, which is reflected with the lower value of the equivalent waves in average for this object. At the same time, we believe that the gas is not over ionized, and so you have an effective driving mechanism for the line, which results in this velocity of the order of few thousand kilometers per second that we measure for these objects. We also measure the mass outflow rate for this object, and here is replotted in the y-axis versus the volumetric luminosity of the AGN. Our objects are the blue one, and this is the red objects are a collection of other broadline region winds from the literature. What we found is that there is a nice correlation between the two, and the slope is very similar to the one that we measure for winds on much larger scale. So if you look at the reddish band, this is winds on kiloparsec scale, and also the yellow band is for winds at kiloparsec scale. The fact that the two slopes are similar, so that there is the same dependency to a fundamental physical parameter from the black hole, may have speculated that the two winds are actually physically connected, the one on the smaller scale and the one on the larger scale. Of course, there is a difference in normalization, and we think that this is tracing the fact that the coupling efficiency in the broadline region is different to what you have on other scales. So to make this point a bit clearer, I hope, I show you here the ratio between the kinetic energy in the winds over the bolometric luminosity. So essentially is a coupling efficiency factor, tell you how much of the energy that you have in the AGN is actually coupled into the winds. And here is the velocity of the winds. And I reported here in green is ultra fast outflows. The outflows are really in the center. And as you can see, they are very fast. And they are also a very high value of this ratio. So they are very efficient in coupling with the surrounding mediums. While the opposite for the broadline region winds, the one tracing carbon-4, and similar also for the granular region winds. And these are lower couple efficiency. We believe that this is mostly due to the fact that the column density in this region are lower of what experienced by the UFOs, and probably also the covering factor is lower, and therefore this results in a less efficient transfer of the energy from the winds to the surrounding medium. Okay, now we should do a jump of few kiloparsec and go in the narrow region. Now we are talking about regions above 1 kiloparsec up to 10 kiloparsec or so. And this is the core of our survey, essentially, because this is what we have been tracing with Symphony through these O3 lines. And on the left, I show you one spectra of one of our targets in which you can see the O3 profile, which is asymmetric, which, as I said, is a clear signature of the presence of gas moving not at systemic velocity, and a broad H beta line. And from this observation from the O3 maps, we can create flux maps, velocity maps, and velocity dispersion map, velocity width map, which are the essential tool that we will use to characterize the properties of the outflow. So before we move to this result, let me give you a more technical note, which is important because what we are after is to resolve spatially these outflows. So we need to be sure that the extended emission that we measure is due to is real, is not just the wing of the PSF that is actually contaminating this extended emission. And so we did several tests to prove that this is the case. A more classic test like the one in the left, in which you have the flux as a function of radius inside the PSF, and this is the gray band here, and the one that we measure on red. And so this is the fact that we have several factors above the PSF is reinforcing our thinking that we are actually observing real extended emission. But we also did more in detail analysis directly on the data cube. So we removed directly the PSF from the data cube. And this is the residual emission spatial result, which is quite significant above 3 sigma level and nicely show the O3 line at the wavelength that we expect. So through this test, we believe we have convinced ourselves that the extended emission that we measure in O3 is actually real. It's not just the PSF. So it means unresolved emission that is spread further out. Okay, now we go to the first question I mentioned at the beginning, and is how common are these outflows? So we want to do a demographic study of the outflows. On the left, it's a collection of our object in red and a collection of literature object in blue, just to show you the nice correlation between the O3 luminosity and the X-ray luminosity we observe, as was already reported. But the most important part is on the right, and here you have the fraction of object for which we measure a certain velocity width of the line. Again, the larger the width of the line, the larger the probability that there is an outflow, the larger the fraction of the gas that is outflowing. So we have been quite conservative. So as I said at the beginning, SUPER was a blind survey, which means that we didn't preselect our target with, to have a higher likelihood to have an outflows, as was done in previous studies. So we didn't preselect the target to have an outflows. We set a conservative cut in the line width of 600 kilometers per second, saying that only above this line width, we believe there is a signature of an outflow. And you can see if you take a normal sample of star-forming galaxies like this one in blue here, all the objects will return full width below such a cut. But instead, if you consider our target, these are in red, you can see that essentially all of them are above this conservative cut. You can appreciate better maybe in the cumulative fraction. So the idea is that essentially almost all, 90% of our objects do show a kiloparsec scale ionized outflow. So the conclusion we take out of it is that the outflows are essentially ubiquitous at this redshift on this gas phase. Now, of course, we want to know that there are outflows, but we also want to know the properties of such outflows. And so this is where most of the challenge comes. For example, we want to know which is the outmass of the outflow. But in order to derive the mass, you need to know not only the luminosity of the line, but also the electron density of the gas. We assume, because we cannot do otherwise at this ratio, that the value of the electron density is 1 for the whole galaxy. But we know that this is a rough approximation. I mean, on the bottom right here, you have an electron density map from a local Seifert galaxy. Here you can do really a spatial result study of the electron density. You can appreciate from the range of colors that you have region you have factor of 2, factor of 2 order of magnitude more range in electron density inside the same galaxy. So this is a strong approximation. Then if you want to convert mass outflow in a mass outflow rate, you need to know also the geometry of the outflows. And so the value that you will derive will depends on the geometry of the outflows. So you have different relation if you consider a biconical outflow, like this one that you have nicely pictured here, or if the outflows is actually expanding as a thin shell. So what we did when we compute the mass outflow rate for our object that you see here on the left was to explore a reasonably wide and well-justified range of geometries and electron density. So if you concentrate here on the left panel, and the red band and the H band are the mass outflow rate that we derive for our object for two different geometry, a biconical outflows in red and a thin shell in H. The message is that the value that we derive actually do not depend much on the geometry. On the other hand, in the range of electron density that we have explored, is down here, there is a huge variation of mass outflow rates derived, depending on the electron density, of course. So overall, what we can say is that the mass outflow rate has a strong dependency with the volumetric luminosity, that is what we expect for a wind-driven scenario, but the values are extremely uncertain due to the electron density that we don't know accurately. On the right panel, we ask ourselves which is the fraction of gas in these outflows that actually can escape the galaxy potential well and go back to the medium. And what we found is that the escape fraction is for most of the outflows of only 10%. So most of the gas would bring back most likely in the host. And finally, to see with which model our observations are consistent, we took the wind model I told you at the beginning, and we plug it in a gas disk of a galactic disk with an exponential density profile. If you do so, then you can predict the velocity of the winds if you know the luminosity of the AGN, the mass of the gas, and the dynamical mass of the galaxy. So here you have the velocity versus volumetric. The observation that we took are the red points, and then the prediction for a range of gas masses are this line that I show you here. As I will show you in a second, we have ALMA observation that allow us to derive the gas mass of this object. And the nice thing is that the gas mass that we derive from this ALMA observation are in the range that allow us to predict to have from this simple model a consistent prediction of the velocity of the outflows. So in few words, the velocity-driven winds is able to reproduce our observation. Okay, now let me move to the second question, the third question we were asking, which is the impact of the AGN feedback on the host galaxy. In one way to put it, and that's been put in the literature in several works, is there a difference in the molecular gas content of AGN host and non-AGN host? So there has been a lot of studies, as I said, low redshift. Essentially, the outcome of most studies is that there is no difference. At high redshift, there are some evidence that the gas, the gas fraction in AGN host seems to be lower, which means that they are gas deficient. We did the same. I mean, for our object, we followed them up with ALMA in cycle 4 and 5. 30 of our targets. We used the CO3 to lime. This is the lower transition we can sample at this redshift with ALMA. And on the left panel, you have in the star formation rate stellar mass plane our object observed, this red object, and the blue is a comparison sample on normal galaxy. On the right, you have a clear detection. We have detection for roughly 50% of our object. So what we did was to compare the CO322 luminosity, a proxy of the gas mass, with the far-infrared luminosity. And this is work by Chiara Circosta for a PhD here at TISO. What Chiara did was to compare our object in red with this match sample from the Phoebs survey, measured in stellar mass, star formation rate at redshift. There is a lot of upper limits, so Chiara did a careful statistical job, and the overlap is very large. So we can say at maximum that there is a 2 sigma tentative evidence that our objects are gas deficient in this plane. Then she looked at the distribution of the ratio between LCO to stellar masses. So if this is a proxy of the gas masses, the ratio is a proxy of the gas fraction. And so in red is our AGN, in blue our comparison sample. And so there is apparently a statistically significant difference in the gas fraction between AGN host and AGN, and hosts do not have an AGN. And finally, Chiara looked at the dependency of the luminosity of the CO as a function of stellar mass. Again, blue, the comparison sample, red, our sample. And especially at a high stellar mass, there seems to be a deficiency in gas in L prime CO. And this reminds us what has been observed in normal galaxy surveys, in which you can see here the reddish point are the one with the 2 show outflows. And this seems to be located mostly at high stellar masses. And as I told you before, we know that all our objects have outflows. So there seems to be a link between the presence of the outflows that we detect in the ionized phase and the deficiency of gas at high stellar masses. Of course, this is not a definitive proof. It could be that also the gas is not removed, but simply excited to higher levels. So that's why it will be very interesting to actually observe the same object with higher CO transition to see that actually this is what is happening. The gas is excited to higher level. But actually, if we go back to simulation, we want to ask ourselves, do the simulation, the same simulation I showed you at the beginning that actually heavily rely on AGN feedback to quench galaxy, do predict that there is a strong negative correlation between gas fraction and bolometric luminosity. And this is work by a new PhD student here at TISO, Samuel Ward. And Samuel looked at a set of simulation, the usual one, TNG, Eagle, Simba. In the bottom panel, you can see he reported the correlation of the gas fraction with L ball. So in this intermediate region, you see that 2 of the 3 simulations actually do not predict any correlation at all. And one actually predicts the opposite, predict that there is a positive correlation. So there is more gas where there is more powerful AGN. Why is that the case? Although this simulation do need AGN feedback to quench galaxy, I mean, there are definitely different explanations. Time scale, the feedback could be the repetitive injection of energy from the AGN on many different cycles. So the L ball is just the instantaneous L ball, so it's not a good measure maybe of that. The quenching could be so quickly that essentially when you have gas depleted, you're not an AGN anymore, so you will not appear in these correlations. Some will look at this a bit more in detail, and on the left you have the distribution of the gas fraction. for the three simulation, in red TNG, in purple Eagle, and in green Simba. So the overall, this is for bright AGN, say above 10 to the 44. Overall, they do not live in gas poor hosts, although there is quite some difference between simulation. In particular, for Simba, for example, there is a predicted population of gas poor AGN hosts. Really, what we learned from this is that the output of the simulation, the prediction of the simulation, strongly depends, as expected, from the recipes that they implemented. To just give you one more example, here is from the TNG simulation, the predicted gas fraction as a function of volumetric luminosity. As I told you at the beginning, there are two feedback modes. There is a radiative mode feedback that is in red, and then there is a kinetic mode feedback in blue. And so you can see that the only AGN that are gas poor actually are this low luminosity AGN. And this is simply because by prescription that they implemented this kinetic mode feedback that is the most efficient one in transferring energy in the surrounding medium kick in only when you go to low accretion rate. This is the kinetic mode feedback. Okay, almost close to the end. We look at also another way to characterize if there was impact on the AGN feedback on the host. And we look at the distribution of star formation in the host. UV tracer of star formation are usually very challenging with bright AGN, so we could not do that. So we resolved to use ALMA, continuum observation in the far infrared to trace the dust and then convert the dust to observe star formation. And these are the dust maps we observed with ALMA for two of our objects. The question we had to ask ourselves is actually this far infrared emission that we are measuring really due to star formation or is contaminated by the AGN emission? If we go back to the SCD I showed you before, this is the red point is the one of the new ALMA continuum observation. And the point I want to make is that if you look at the prediction of how much dust is due to the AGN emission, that is, for example, the so-called torus, this is negligible, few percent of it. This is the green line. As well as you ask yourself, which is the contribution from synchrotron emission, this is also negligible at this wavelength. So we do believe that the infrared emission we measure with this observation are mostly due to star formation. And so we can effectively use these maps to trace star formation in a spatially resolved fashion. And these are the maps I show you here for three objects. So the white contour are the dust contour that now you can think also as a star formation maps. And at the bottom, the color maps are the outflows that we trace with the O3, the ionized outflows. So what we see essentially is that there is no clear impact of the outflows on the distribution of star formation. I mean, we don't see clear holes in the presence of dust and so star formation where the AGN is flowing. Of course, there could be some impact, but on a smaller scale that we're able to resolve. We are not able to resolve below 2 kiloparsec. Or could be also that we are using the far infrared. As you know, the far infrared is averaging the star formation history on 100 million years. So if the impact is much more on shorter time scale, then you want actually to have a different tracer that is sensitive to shorter time scale also star formation, so that you don't dilute the effect of the AGN looking at very far back in time. Okay, so finally going back to the original picture and moving to larger scale, as I say, that there is the idea that these AGN feedback outflows can actually pollute the CGM, the circumgalactic medium, so hundreds of kiloparsec scale around the galaxy with metal-rich gas. And we think maybe we observe this in this object. One of our targets has been observed with the ALMA compact array. The ALMA compact array allows you to trace very effectively diffuse and large extended emission. And do we see this very extended 100 kiloparsec scale CO emission? So we think this is a very large molecular reservoir around this AGN. And we don't see cluster of galaxies, neither other object at the same ratio that could justify such an extended CO emission. And this is show you the CO flux as a function of distance, and you can see as most of the flux is on scale of 100 kiloparsec. So we ask ourselves, what is the origin or what is contributing to this large gas reservoir? We look at the kinematic maps of this gas, and although the synchronosis is quite poor, as you can see, we don't see clear rotation structure. So one idea is that actually it's the outflows that is disturbing the structure, I mean, creating these turbulent motions. And the CGM can actually cool thanks to the outflow itself. This has been observed, for example, in this Lyman alpha observation of a quasar redshift of 3 observed in Lyman alpha. So one idea is that the outflow itself is actually accelerating the cooling of the gas in the CGM and forming this large molecular gas reservoir. And before finishing, just a jump into the future, possibly near future. One thing I mentioned at the beginning is that these outflows are multi-gas phase. Until now, we have been tracing for this object just the ionized gas phase, but it will be very important to trace also the molecular gas phase. And you can clearly see the importance of it from this panel, in which from a simulation by Tiago Costa, you have the mass outflow rate as a function of distance from the center of the AGN in different gas phases. So the hot gas component will be observed probably by Athena, but not before that. But then the warm component is the one we observe with Symphony, and we already know. But as you can see in blue, there is this cold component, this cold molecular component that could be as important as the ionized component, and we cannot observe currently with ALMA. At least it's very challenging to do. So one way we are trying to do that is through JWST, in particular with Mainieri. We have a program inside of one to observe 3 of our targets, and we will use these raw vibrational lines, these H2 lines that are observed in the mid-infrared, and so accessible by Mainieri, but not from the ground, to trace this molecular component. And this will be crucial because we will then have the total gas mass in the outflows, not only the ionized phase. As a byproduct, we will be observing also PAH feature, and this could solve the other problem we have. PAH would be the long-seeked good short time estimator for star formation in AGN. We know this is done local galaxies, so local AGN, so we would hope to do the same in this redshift 2 object. And this will allow us to trace star formation on the same time scale of the AGN. And finally, another project that we want to expand. Our survey is to that study on one CGM, large molecular gas reservoir, is just for one object. In order to understand what is the physical mechanism that actually is creating this gas mass, we need to have statistics. So we are trying to get more observation both with MUSE and ALMA of other targets for which we know that there is an outflows. And we want to see how the properties of the CGM is related to the properties of the outflows that we have observed. And I slightly run out of time, I'm afraid. So I just put the conclusion. Yes, I've been presenting you the result from our survey that has been recently completed. And going back to the 3 questions I put at the beginning, I think we have done some progress in them, although we don't have the final answer for all of them. So we know for sure that outflows are ubiquitous at this redshift. As for the driving mechanism, there is a strong indication that a wind-driven model can reproduce our observational result, so it seems to be a favorite model. In terms of impact, here there is a conflicting result. We seem to observe deficit on the molecular gas, but in terms of star formation, we do not see clear signature of dust or star formation suppression. And that's all. Thank you.
Thank you very much, Vincenzo.